Okay. Let me just make sure that there's nobody else waiting. I didn't see anybody. Nope, it's just the two of us, I think. Yep, that's all I see so far. Okay. All right. Let me do some fiddling around here. Move the taskbars out of the way because they're blocking view. And I'll also move us a little bit out of the way. Okay. And I think I'll go on and set up the whiteboard, because that's what we'll be using mostly today. And move this over and to the left and up. Okay. I don't know why it's not cooperating much today. Okay, there we go. All right, there we go. Now, so if there are no questions, I guess we can, my clip on my pocket just keeps, let me see if this will work any better. That may work a little better. Okay. Okay. So I think I will go back to the PowerPoint, well, not PowerPoint, the textbook, and then we'll come back to that. All right, where we left off last time, if there are no questions on anything so far today, we are in Chapter 4, Higher Order Differential Equations, Section 4.1, specifically 4.1.2, I believe it is. Yep, 4.1.2. And we're on page 124 talking about linearly dependent sets of functions. Okay, so here is where we are, and we're going to do example 6 here. Here is a set of functions. f1 of x is the square root of x plus 5. f2 of x is the square root of x plus 5x. f3 of x is x minus 1, and f4 of x is x squared. Okay, now they say that set of functions is linearly dependent on the interval from 0 to infinity. Now, let's pause for a moment here and see why we say 0. You cannot put x negative. So technically, x could have been 0 here, I think. I see no reason why it couldn't be, but they started with not counting 0, but 0 to the right. Certainly, x can't be negative, okay, because the square root of x would not be defined. Square root of x would not be defined here either. So we're only going to deal with positive x's. Okay, now, what I think I'm going to do here is give you an illustration. They just say this, and then they don't. I found it a little less than satisfying how they approach this. So I'm going to move us back over here again, and if I can find my pen and my pad here, here is a set of functions. Okay, yuck, this is so aggravating. Okay, f1 of x is equal to the square root of x plus 5. Wait, that's not right. Okay. It's the square root of x plus 5. Square root of x is one entity there. Okay, f2 of x is equal to the square root of x plus 5x. Goodness gracious, this thing is so aggravating. Okay, the square root of x plus 5x. Okay, I did it again. The f3 of x is equal to x minus 1, and f4 of x is equal to x squared. Okay, now it says it's linearly dependent on the interval. Okay, now I'm going to show you how you can determine that. Okay, remember what do we mean by linear dependence? That means there is some set of parameters, C1, C2, C3, and C4, such that C1 times F1 of x plus C2 times F2 of x plus C3 times F3 of x plus C4 times F4 of x okay, is equal to 0 without all four of those c's equaling 0. Okay, now let's plug and chug. F1 is this plus this, so what we have here is C1 times the square root of x plus 5C1. Okay, that's C1 times this plus C1 times that, plus C2 times the square root of x plus C2, let's put it as 5C2 times x plus, and C3 is C3x minus C3 plus C4 times x squared. Now, we've got to see if we can come up with a set of c's, not all equal to 0, that makes that true. Not all equal to 0. All right. Now, you have, for your variable, you might say square root of x, you have that C1 square root of x plus C2 square root of x has to equal 0. Okay? Has to, because otherwise, I mean, you can't get rid of the square root of x unless those two is equal to 0. And remember, x, the square root of x, cannot be 0. I didn't write that down, but x is between 0 and infinity. Okay, so x can't be 0. So the square root of x cannot be 0, and since C1 square root of x plus C2 square root of x has to equal 0 because there is no square root of x over here, C1 plus C2 has to equal 0. Okay, now constant terms, 5C1 minus C3, that also has to equal 0. Okay, so 5C1 plus C3, that has to equal 0 because those are your constant terms here. Okay, yeah, that's a minus C3, sorry about that. Okay. Okay. 5C1 minus C3 also has to be equal to 0. Okay, we've already got this one covered, that one covered, that one covered. Here we have a 5C1 plus C3 has to equal 0. That's 5C2, sorry. Yuck. 5C2 from this term plus C3 has got to equal 0. Okay? Those are your x terms. So we've taken care of this one and that one. We've taken care of this one and that one. Now we've taken care of this one and that one. And all we have left is that C4 has got to equal 0. Well, the only way that can happen is C4 is equal to 0. So that's out of there. C4 is equal to 0. So now we have 3 equations, 3 unknowns. Let's see what happens to that. Now, Kira, I know you do matrices because you're in linear algebra. Let's do it using matrices, okay? Now, the others, 2 in the class that don't have linear algebra yet, I don't think they have, they may find this a little less than satisfying, but let's see what we've got. We've got 1, 1, 0, 0. C1 plus C2 plus 0 C3 is equal to 0. Okay? Now, 5C1, that would be a 5, 0, no C2, minus 1 is equal to 0. Okay? Third equation, 5C2, 0C1, 5C2 plus C3, 1 is equal to 0. Okay? And we don't need to even write this one down because C4's got to equal 0. Okay. Okay, what are we going to do? Minus 5 row 1 plus row 2. Okay? So we're going to leave row 1 alone. 1, 1, 0, 0. Row 2 would be minus 5 times 1 is minus 5 plus 5 is 0. Minus 5 times 1 is minus 5 plus 0 is minus 5. Minus 5 times 0 is 0 minus 1. And this one's a 0. Okay? Now, this is already a 0 here, so we're just going to do 0, 5, 1, 0. Okay. Now, pretty obvious to me, you can add these two together and you get a row of zeros. So basically what we wound up was 1, 1, 0, 0, 0 minus 5, minus 1, 0, and 0, 0, 0, 0. What we're doing here is row 2 plus row 3 is the new row 3. And that goes all zeros there. So what do we have here? This is your arbitrary parameter here. So let C3 equal T. Okay, then this gives you minus 5 C2 is equal to T. So C2 is equal to minus 1/5 T. And then C1 C1 plus C2, which is, let me, okay, C1 plus C2, which would be a minus 1/5 t, is equal to 0. Okay, and that makes C1 equal 1/5 t. Well, let's multiply each of those by 5, and you get C1 is equal to 5t, no, is equal to t, sorry, equal to t. C2 is equal to minus t, and C3, multiply that by 5, and you get 5t. Okay, now what do we conclude here? C2 and C1 are just opposites of each other. Okay, so therefore they are linearly dependent. Okay, now what they say here is F1, like t equal 1, C2 would be minus 1, so that would be t minus t plus 5t, okay, plus 0, okay, that is a linear dependent. Okay, so let's go on to the whiteboard, to the book, and see how that works out. Okay, what they said here, and I'm going to move us up here again. What we have here is that F2 is a linear combination of F1, F3, and F4. F4 is 0, so the C4 is 0, so don't have to worry with that. But F2 is equal to F1 plus 5 F3, and you got it for every x in the interval. That's going to be the case. Now, linearly dependent. Okay, now let's think of another way to look at this: solutions of differential equations. We are primarily interested in linearly independent functions, or more to the point, linearly independent solutions of a linear differential equation. Although we could always appeal directly to the definition, it's awkward. Okay, it turns out that the question whether a set has n solutions of a homogeneous length order differential equation is linear independent can be settled somewhat more mechanically by using a determinant. Okay, and you're also in linear algebra, which you're using determinants now. So here's what we're going to do. Suppose that we have these functions f1, f2, f3, f4 up to fn, and that this possesses at least n minus 1 derivatives. Okay, now the determinant we're going to name w. There's a reason for that, and this w is a function of these functions f1, f2, f3 up to f sub n. How is it related? Well, it's the determinant of, you write them here, f1, f2, f3, f4 up to f sub n. Second row, f prime of 1 plus f prime of, not plus, f prime of 2, f prime of 3, all the way up to f prime of n, and then f double prime of f double prime, f1 double prime, f2 double prime, f3 double prime, all the way up to f n double prime. And then finally you get to the n minus first derivative f sub 1, n minus first derivative of f sub 1, n minus first derivative of f to 2, n minus first derivative of f sub 3, all the way up to n minus first derivative of f sub n. Write those as the determinant. You have n columns and you have n rows, because this is the 0th derivative, okay? First derivative, second derivative, up to n minus 1. That makes it n. So you have a square matrix, n by n. Okay, now what we're going to do with that is take that determinant, and that's, they're naming w, the primes denote derivatives. That's called the Wronskian of those functions. The Wronskian determinant was named after the Polish philosopher and mathematician Józef Maria Hone Wronski. Okay, I don't know if I'm botching his name terribly, but he lived 1778 to about 1853. So that was right after the Revolutionary War here in the U.S., up to just about the time of the war between the states here in the U.S. Not quite. So he lived, 50, 60, 70 some years. Okay. All right. So here's the criterion for linearly independent solutions. Let's let your y1, y2, y3 be n solutions for a homogeneous linear nth order differential equation. So it's an nth order equation, you have n solutions. Okay? Now, this is your homogeneous equation. Okay, that was equation 6. On some interval I, have to define the interval. Then the set of solutions is linearly independent on that interval I if and only if the Wronskian is not equal to 0 for every x on the interval. Okay, every one of them. Okay, now sounds like a tall order, really isn't quite as hard to do. Now here comes James. Good deal. We got James here. Let me mark him present. All right, we got number 1 and number 3. Still missing 2, 4, and 5. Let me make sure. Hey, how you doing? Yeah. Okay. We had trouble getting on, period. I had power go out here. I mean, I had logged on, had Zoom was up, and I had a couple minutes before the time for it to start, and I was just getting set up, and then all of a sudden we had a flick in power. Okay, well, I thought no big deal, except when it flicked the power, I lost internet. Okay, and then I spent most of the rest of the 15 minutes trying to get internet back again. So you didn't miss a whole class, you missed part of a class, but boy, it's tough. Let me also say this. I've said it before, but you weren't here maybe when I said it. You know what Tuesday is, right? Election Day. I hope that you're registered to vote. If you are registered to vote and you haven't voted yet, please, please don't forget to vote. Now, we only meet Monday, Wednesday, but our linear algebra class meets on Tuesday. So if you have to go during that time, go, but get back as soon as you can so we'll have class. But if you can arrange it till you can vote, the polls are open 7 to 7. If you can get by and vote outside of class time, that would be fantastic. But even if you have to miss class, it's worth it to vote. Get back as soon as you can and we'll pick up class. All right, good deal. Now, we were just talking on page 124. This is chapter 4, higher order differential equations. 4.1 is preliminary theory linear equations, okay? And we've just done example 6, and we're doing the definition of the Wronskian and the theorem, 4.1.3, bottom of page 124, okay? Now, what is the Wronskian? That's if you had n functions, L sub 1, L sub 2, L sub 3, all the way up to L sub n, okay? And these n functions possess at least n minus 1 derivatives. So every one of them has derivatives up to and including the n minus first derivative. They don't have to have the nth derivative, but up to the n minus first. The Wronskian is that set of functions is the top row. The second row is the first derivative of all those functions. The third row is the second derivative of all those functions, all the way down till you get to the n minus first derivative of each one of those functions. Take a determinant of that square matrix. Once you get that determinant, that's called the Wronskian of the functions. And here's what the theorem says. If that y1, y2, y3, all the way up to y sub n are n solutions for this homogeneous linear nth order differential equation, that's number 6, that's the homogeneous one, on some interval I, then the set of solutions is linearly independent on that interval I if and only if that Wronskian right there is not equal to 0 for every x in the interval. Every x in the interval. Okay? So there we're kind of melding our linear algebra with our differential equations because we're doing a determinant. Okay. Now what did I just do? Okay. Didn't know it would do that, but let me scroll down and make sure I did it right. Yeah. Okay. It follows from that theorem that when y1, y2, y3, all the way up to yn are solutions of your homogeneous linear nth order differential equations, okay, on the interval I, the Wronskian is either identically 0 or never 0 on that interval. Thus, if we can show that the Wronskian is not equal to 0 for some x of 0, then the solutions are linearly independent on that interval I. Okay? Now here's a couple of pretty hairy looking problems here. y1 is cosine 2 log x over x cubed. y2 is sine 2 log x over x cubed. Okay? Now, two functions, they should define, excuse me just a second, I think I've told you all before, I'm really anemic still. I'm feeling a little better just about every day, but still I'll just run out of energy, especially this late in the day. So excuse me just a minute. Let me get a sip of caffeine with sugar so maybe I can go a little bit longer. All right, sorry about that. Okay, two equations, y1, y2, second order differential equations. What we want to see if these two functions are linearly independent or not. Okay, now what we need to do here is make sure these are solutions for this differential equation. So I can't write here, so let's go to the whiteboard where I can write, and we'll clear off this one. Any questions before I clear it? That was the previous example. Okay, now I'm going to move y'all, okay, there. Now, kind of hairy looking functions. y1 of x is equal to cosine of 2 log x, okay, divided by x cubed, y2 of x is equal to sine of 2 log x. Yuck! Log x divided by, sometimes it won't write at all, sometimes it writes wherever it wants to, x cubed. Okay. Now, they claim this is a solution, these are solutions for this differential equation. X squared y double prime plus 7xy prime plus 13y is equal to 0. Okay, a homogeneous second order linear differential equation. Okay, linear because the coefficient here is only a function of x, coefficient here is only a function of x, coefficient here is a constant, no function, no y in that. Okay, so what we better do is find out, oh boy, this is going to take a while. Okay, what is y prime, y1 prime? Okay, that's going to be a quotient rule at best. Okay, you could do it as a product rule. Which would you prefer, quotient or product? I really don't care too much. Which do you prefer, quotient or product? Anybody? Well, let's go with quotient rule since it pretty much is a quotient. Okay, low d high, that would be x cubed times the derivative of your numerator. Well, the derivative of cosine is minus sine of 2 log x okay, times, okay, chain rule here, 2 over x, derivative of this part, okay, so that's low this times derivative of the numerator, minus high, that's the cosine of 2 log x, derivative of the denominator, which would be 3x squared. Okay, all divided by low, which is x to the 6th. Okay, now we need to do the second derivative, y1 double prime, and this is really getting nasty. Okay, now the book didn't say we had to do this, but this is really getting nasty. So let's just take a time out and say we'll take their word for it, that these are solutions. Okay, I wasn't going to do that, but it looks like we almost have to. Okay, because we would take up most of the rest of the class just verifying this. So let's do that. Okay, so we're going to erase these and just take their word for it that these are solutions for that differential equation. Okay. I'm so sorry. All right. Now, so these two are solutions. What we have to do now is figure out whether they're linearly independent or dependent. Okay. Now, I sort of wish I had left what I had started right there, but let's do it. The Wronskian for these two would be the determinant of the functions themselves, cosine of 2 log x over x cubed sine of 2 log x over x cubed Okay, now we need to take a first derivative. That's what we were doing, and like I said, I kind of regret that I didn't put that in here, but let's take the first derivative of this, and that would be low x cubed d high, okay, which would be derivative of this, which would be a minus sine of 2 log x times 1 or 2 over x. So I'm going to put the 2 here and then make this an x cubed here. Is that right now? Let me think a moment. I think that's x to the 4th now. And then we have x to the 4th times x cubed would be x to the 7th, I think. That's x to the 6th. Okay. Yuck, this is a pain in the neck. Okay. I think what I'm going to do, just because it's so messy, okay, let's take the first derivative of this. I almost had it before, but I decided to quit. I wish I hadn't. The y1 prime is equal to low d high x cubed times derivative of this, which would be a minus sine of 2 log x times 2 over x. So I'm going to write this here, 2 over x, okay? And we've still got to do the minus cosine 2 log x times 3x squared. I'm going to put the 3 here and the x squared here, and all that is over x to the 6th. All right. Boy, what a pain. What a pain. Okay. Now, rather than go through this in all this gory detail, let's just go back and see. Okay. I'm going to let the fingers do the walking here. Okay. That was, here is your low, okay. Yuck. Okay. You see here, the 1 over x here cancels out one of the x's here. So this gives you a minus 2 x squared times the sine of 2 log x. So in other words, we got a minus 2 from here, x squared from those two terms, sine of 2 log x. Okay, and that's over x to the 6th. And here we have a minus 3 times x cubed, okay, times the cosine of 2 log x, okay. Now that was a mouthful and a half, okay. So let's see if that's indeed what we come up with here, okay. Got to move y'all out of the way again. Okay. Minus 2x squared sine of 2 log x minus 3x squared cosine of 2 log x all over x to the 6th. Well, here you have an x squared, there you have an x squared, so you could lose those two and just have your, let's see, reduced form, I would say, okay. And then when you do the same thing here, this gives you a positive 2x squared cosine 2 log x minus 3 x squared sine 2 log x, and again that's over x squared. Factor out an x squared here, and this gives you over x to the 4th, just like this gave you over x to the 4th. So rather than expanding that unwieldy determinant, we just choose a value, okay, a value, x equal 1. Well, log of 1 is 0. Cosine of 0 is 1, okay. 1 is, 1 cubed is 1. Now this will give you a 0 over here because the log of 1 is 0, sine of 0 is 0, okay. And then when we put the 1 in here, that's this goes to 0 because log of 1 is 0, sine of 0 is 0. This goes to minus 3 okay. All right. I hate to just shortchange this, but it really is so awkward, okay. But when you do that and put the x equal 1, this would be a 1, that becomes a 0, this becomes a, this term right here becomes a 0, okay. All right, yuck. X equal 1, that's a 0, this is a okay. That becomes a 0, this becomes a minus 3 over 1. So this is a minus 3, that's where that comes from. This becomes a 2, that goes to 0. So here we have 1, 0, negative 3, 2. Okay, now how they got away with that is if it works for any value, it should work for them all. They just chose judiciously x equal 1, so this would be a 0, that would be a 0, that would be a 0, that would be a 0, this would be a 0, that would be a 0. But you're taking, oh, here's Jemanuel. Let me get him here if I can get it to link on him. There we go. And let's get Jemanuel present. All right, we got 1, 3, and 4 now. Okay. Now, Jemanuel, we're in Chapter 4, Higher Order Differential Equations, Section 4.1, Preliminary Theory, Linear Equations, and specifically in 4.1.2, which is Homogeneous Equations. We're on page 125, doing the Wronskian, which we have defined a little bit ago, and it's a determinant. Now I know, I can't remember, have you had linear algebra, Emmanuel? You have, okay, so you know what about determinants. Yeah, so let's take the determinant here. 1 times 2 is 2, minus 0, that's 2. As long as that Wronskian is not 0, these are linearly independent. Okay? Now, this is a long step from that, but it's a legal step to do. Okay? The fact that that is not 0 is sufficient to conclude y1 and y2 are linearly independent on that interval from 0 to infinity. Now, obviously, you can't include 0 in this because you can't take the log of 0. But anything greater than 0, you can take the log of, so that's okay. All right. Now, let's move to another definition here. The set of n linearly independent solutions of a homogeneous linear nth order differential equation is given a special name. Now, what's required here? Okay, first, you have an nth order differential equation. Number 2, you have n linearly independent solutions for that homogeneous linear nth order differential equation. So if you have the n linearly independent solutions of that nth order differential equation, we name that the fundamental set of solutions. Any set, y1, y2, y3, all the way up to y sub n, of n linearly independent solutions of a homogeneous linear, they did it some last night, okay, that's called the fundamental set of solutions. The basic question of whether a fundamental set of solutions exists for a linear equation is answered in this theorem. Okay? There exists a fundamental set of solutions for the homogeneous linear nth order differential equation 6, that's a homogeneous, okay, on the interval I. There always does. If you have linear nth order differential equations, there is always a fundamental set of n solutions, okay? Always. Other types, no, but linear, yes. Now, analogous to the fact, let me scroll on down a little bit lower here, analogous to the fact that any vector in 3 dimensions can be expressed as a linear combination of the linearly independent vectors I, j, and k, any solution of an nth order homogeneous linear differential equation on some interval I can be expressed as a linear combination of the n linearly independent solutions on I, that fundamental set. In other words, n linearly independent solutions, y sub 1, y sub 2, y sub 3, all the way up to y sub n, are the basic building blocks for your general solution for the equation. Okay. That said, let's move to the next theorem here. Theorem 4.1.5. Okay. If you have those n solutions, y sub 1, y sub 2, y sub 3, all the way up to y sub n, and they are a fundamental set of solutions for the homogeneous linear nth order differential equation, that's 6, the homogeneous one, on that interval I, then the general solution of that equation on that interval is C1 is equal, y is equal to C1 y1 of x plus C2 y2 of x plus C3 y3 of x, all the way up to, okay, where the C1, C2, and all these are arbitrary constants, not all equal to 0 generally. Okay. This theorem, right here, states that if y of x, now why they threw in a capital Y of x, is a solution of the homogeneous linear nth order differential equation on that interval, then the constant C1, C2, and C3 can always be found so that y of 0 is some linear combination of all those constants. Okay, now they go through a little proof for 2x2s. Okay, I think I'm going to have to get some caffeine, sorry. Okay, so here's the proof that they're getting to here. And basically what they're doing, they're showing that those solutions and their derivatives, the determinant of that, not equal to 0. Okay, but that's simply the Wronskian. Okay, and if it's not equal to 0, those are uniquely satisfied. So g of t, c1y1 of t plus c2y2 of t equal k1, that's this function, and g prime of t, c1 y prime of t plus c2 y, those are our solutions. Okay, and with that being the case, they have to be a unique solution. That's basically what they're getting down to. So the y of x satisfies the same linear equation and the same initial conditions. Because that solution of the linear initial value problem is unique, we have that y1 is equal to y of x is g of x, y2 or yx is equal to c1 y1 plus c2 y2. Okay, it almost feels like they're running around in circles here, but don't let it dissuade you. Let's look at example 7 here. These are a lot easier to deal with, okay, than those last ones. So let's go to our whiteboard. All right. I think I'm going to have to turn on my ceiling fan. It has gotten warm and muggy. I think that may help a little bit. I think I told you before, I'm still really anemic, so I just run out of energy so fast, especially this late in the day. So let me move up y'all here, sorry about that, and clear the drawings here. Okay. Oh man, I'm rapidly running out of energy totally. Okay, we're over on page 126 now. Example 7, bottom of page 126. Okay. Here are some functions. y1 e to the 3x. Good old function, e to the 3x. Okay. y2 is equal to e to the minus 3x. Okay. Now they claim these are both solutions to the homogeneous linear equation y double prime plus 9y is equal to 0. Okay, and they say these are good anywhere from minus infinity to infinity. Okay, certainly e to the x and e to the minus x are defined everywhere. Okay, now let's go back to sort of what we were doing before, and I just can't keep this clip hanging in place. Okay, now let's first do your y1 prime. This is so much easier than the last one. y1 prime is equal to 3 e to the 3x. y1 double prime is equal to 9 e to the 3x. y2 prime is equal to minus 3 e to the minus 3x, and y2 double prime is equal to 9 e to the minus 3x. Okay, now with those done, let's plug these in here. Okay, each one of them. Okay, so y double prime here is 9 e to the 3x plus, okay, something seems to be wrong here. Is that a plus or a minus? It's a minus. That's what's wrong. I said that can't be true. Okay, get my eraser. Why in the world? There we go. That is a minus there. Okay, minus 9y. So this would be 9e to the 3x, y double prime, minus, yuck, I needed to erase that one too. Okay, minus 9e to the 3x. That's certainly equal to 0. Let's do the other one. Y double prime would be 9e to the minus 3x. That's y double prime minus 9 times e to the minus 3x. And sure enough, that's equal to 0. Okay? For every x in the domain. Okay? Now, whoa, here comes Ryan. Good deal. Now we got 4 out of 5. I've just lost my clip again. This is so aggravating. Okay, and let me get Ryan marked present. So we're only missing Jesus or Miguel. Okay, let me make sure I haven't left him hanging out here somewhere. Nope, don't see him. In fact, we've lost somebody, didn't we? I think we lost Jemanuel. Okay, so hopefully he'll be back. All right. Now, so we verified both of these are solutions. Okay. Now, what we're asked to do, these two functions are both solutions that homogeneous linear differential equations on the interval minus infinity to infinity. Okay. What we have to do by inspection of the solutions are linearly independent on the x-axis. Okay. Now we know that's true because if we were to graph those, got my pen upside down. If we were to graph these, this one would be coming along like this, and this one over here would be coming down like this. So obviously not dependent on one another. So they're linearly independent. That's what I mean, obviously, by inspection. Okay. Now, we can also do our Wronskian. Okay. And Ryan, what a Wronskian is a determinant of your functions e to the 3x, e to the minus 3x, then the derivative of the function, which is 3e to the 3x minus 3e to the minus 3x, take the determinant of that. Now I can't remember, have you had linear algebra? You have, haven't you, Ryan? Oh, you have not. Okay. What a determinant is when you set up a matrix like this, you do a cross product here. The top times this, that would give you minus 3. Now e to the 3x times e to the minus 3x, this is 1 over e to the 3x. That's just 1. So that gives you a minus 3 here. And when you do the up diagonal, it's the opposite of that. That would be minus 3 again. This is minus 6. Minus 6 is not equal to 0. Okay, so therefore we know these two functions are linearly independent of each other. Okay, that's what the Wronskian tells us. Okay, now since that's equal to minus 6, we conclude that these form a fundamental set of solutions, and that consequently any linearly independent combination of those will also be, that will be your general solution. So your y, the general solution, would be c1 e to the 3x plus c2 e to the minus 3x. Okay, there's your general solution. Okay, good everywhere from x equal negative infinity to positive infinity. Okay, let's move on to example 8. All right, I think I'll go back to the book for a moment here, and then we'll probably go back to the whiteboard. Here's example 8, just a little bit scooted down the page from where we were. And let me move y'all again up here. Okay, here's example 8. All right. Here's a function. Y is equal to 4 hyperbolic sine of 3x minus 5 e to the minus 3x. Okay. Now, frankly, I don't care for hyperbolic sines. What I'm going to do is write this in what it really is. Okay. That's a solution for the differential equation in example 7, the one we just did. Okay. This one here. Well, this right here. There's your solution. That could be written as without the 4 there, but you got it. Okay. It's a solution of the differential equation. Okay, it says verify that. So let's do that. Okay. Yuck. We may not have time to finish this one. I was thinking this would be a bit shorter. Okay, I'm going to move y'all again. Okay, and we're going to clear the drawing here. Okay. Here is at least the setup for example 8. Here's a function. Y is equal to 4 times the hyperbolic sine of 3x minus 5 times e to the minus 3x. Okay? And they claim that is a solution of the differential equation in example 7. In example 7, that differential equation was y double prime minus 9y equals 0. Now, I don't like messing with hyperbolic sine. Okay, so what I'm going to do, I think I'm going to do it. Let's see if I got the resources here to do it. Yuck. I thought it was here in the front of the book, and it's close but not quite. Okay. But I do think they give it to you. Let me just check and make sure. Laplace transforms. Okay. All right. Now, here's what hyperbolic sine is. Okay. I'm going to come over here if I can get my pen to move. There we go. Okay. Hyperbolic sine of 3x is defined to be e to the 3x minus e to the minus 3x. This is so aggravating. Okay. Divided by 2. Okay. And this is the whole reason I do this. That is so much easier to work with than trying to remember the rules for taking a derivative of hyperbolic sine. Okay? Just use the definition. Okay? So I'm going to rewrite this equation to be this. Y is equal to, this equation here, 4 times e to the 3x minus e to the minus 3x over 2. Okay. That's what hyperbolic sine is, 4 times it. Then we'll do minus 5 e to the minus 3x. Okay. So if you write it that way, this becomes, well, 4 divided by 2 is 2. So this will be 2e to the 3x minus 2e to the minus 3x minus 5e to the minus 3x. Okay, well, combine like terms there and you get 2e to the 3x minus 7e to the minus 3x. Okay, so much easier to work with. This is your y right here. Okay, now let's take a derivative of that. Okay, this is your y. So let's do your y prime. And this would be 6 e to the 3x plus 21 e to the minus 3x. There's your y prime. Y double prime would equal 18 e to the 3x minus 63 e to the minus 3x. Okay, now put these together. Y double prime, which would be this, minus 9 times this, so that would be minus 18 e to the 3x, and then minus 7 times minus 9 would be plus 63 e to the minus 3x, and sure enough, these add to 0, these add to 0. So that is equal to 0. So we've just verified that this right here is a solution for that differential equation. All right. 3 minutes. Let's see if we can go that. Okay. In view of theorem 4.1.5, we must be able to obtain that solution from the general solution. Y is equal to C1 e to the 3x plus C2 e to the minus 3x. Okay. Now, remember our last thing said that y is equal to C1 e to the 3x plus C2 e to the minus 3x. Okay? Well, look at that. If you let C1 equal 2, C2 equal minus 7, there you have it. Okay? So the last expression is recognized as that thing we had to begin with, but that's exactly what we have here. So, sorry. All right. Now, we got 2 minutes. Can we do example 9? Okay. Let's see if I can clear this. Let's see if we can do example 9. Here's some functions. y1 is equal to e to the x. y2 is equal to e to the 2x. y3 is equal to e to the 3x. I'm so sorry. Now, they say those functions satisfy the third order differential equation. Okay, let's try it. Y triple prime minus 6y prime, is that y prime or y double prime, plus 11y prime minus 6y is equal to 0. Now they claim these three functions satisfy that. Okay? Let's see if we can make that happen. y1 prime is equal to e to the x. Okay? y1 double prime is equal to e to the x. Okay? I love this one. y1 triple prime is equal to e to the x. Okay? If you were to put that in, this would be e to the x minus 6e to the x plus 11e to the x. That would be minus 5 plus 11. That's plus 6e to the x minus 6e to the x. That's equals 0. Yes, that one works. Okay? Let's see if this one does. y2 prime is equal to 2e to the 2x. y2 double prime is equal to 4e to the 2x. And y2 triple prime is equal to 8e to the 2x. Okay? So y2 triple prime would be 8e to the 2x minus 6 times 4 is minus 24. So 8 minus 24 would be 16, I think. Okay. Plus 11, 22. That would be plus 6 minus 6 e to the 2x. Sure enough, that adds to 0. Let's see if the third one works. y3 prime is equal to 3e to the 3x. y3 double prime is equal to 9e to the 3x. And y3 triple prime is equal to 27e to the 3x. Okay, this is going to get hairy here. So here we have 27e to the 3x minus 6 times 9 is 54. That would be a minus 27e to the 3x plus 33. So minus 27 plus 33 would be plus 6. Minus 6 adds a 0. So all three of those are solutions for that differential equation. Okay, we've run out of time. Okay, now what we'll do next time is pick up from where we left off here, and we will do the Wronskian just to show that indeed these are linearly independent. Okay, we've already shown their solutions. Now we have to show that they're independent, and once we do that, we will be ready to go. We almost finished 4.1.2. Here's homework exercises in that. Okay, let me get my page in place here. Okay. All right. Homework exercises beginning on page 130. Any of the odds in 4.1.1, 1 or 3, 5 or 7, 9, and 11. 13, that's in 4.1.1. 4.1.2, any of the odds 15 to 21 and 23 to 29. Okay, now if you can't do all those, hang on till we finish that last example. You should pick that up, and then we'll pick up in 4.1.3 and wrap up 4.1. This is a long section. These preliminary theory sections always take so long to do, but the next section, 4.2, is very, very short, so we should be able to get that done easily. Well, we'll try to do 4.1.3, and well, that's going to take a while, so we'll see how it goes. Any questions in 4.1? Okay, well then I'm going to stop sharing. Sick and tired of sharing here, and unless there's some questions, I'm going to end the recording for us all. So folks, I think I've said this before. Ryan, you weren't here, I don't believe. What is Tuesday? Election day. Okay, now I hope you're registered to vote, and I hope you've already voted, but if you haven't, please don't forget to vote on Tuesday. Okay, so important that we vote. It's fundamental to what we stand for as a nation, so please vote. Okay, won't interfere with this class because we meet Monday and Wednesday. James and Kira, they have class on Tuesday and Thursday, but hopefully either they've already voted or they can work that out. But please vote. Okay, now if you have classes on Tuesday, it could be pretty shaky on the internet, because I bet you, my wife was saying, everyone in the world is probably going to be checking out as much as they can on the internet on Tuesday. It may get really unstable. Hopefully not, but we'll see. So please, folks, remember to vote on Tuesday if you haven't already, and we'll see you, James and Kara, we'll see you tomorrow, and Ryan, we'll see you on Monday. Okay? Any last thoughts, parting shots? All right, let's end the meeting for us all. We'll see you Monday, or tomorrow or Monday.